Hello, my name is Shane, and this is my video submission for the Week 6 module for the CSE 310 course taught at BYU-Idaho. The module that I have selected for Week 6 is the Choose Your Own Adventure module. To be specific, I have decided to choose the Intro to Machine Learning course taught at Kaggle.com. I don't have any prior experience with machine learning, but I do have a very strong grasp of the Python programming language, and I wanted to take this course because I'm specifically interested in pursuing data science and potentially in the future artificial intelligence and machine learning. To demonstrate my understanding, I'm supposed to write software, and the software that I've decided to write is a improved submission for the housing prices competition that Kaggle users are first exposed to after they take the Intro to Machine Learning course. The first submission that you submit typically has a mean absolute error score of around 21,000, and my goal for my model was to work on improving it so I would have a significantly better score. So first things first, we are going to start by writing the model for the prediction. And we're going to import a couple libraries and a couple functions from those libraries. So we're first going to import pandas as PD, of course. And then we're going to import three things from the sklearn library. So from sklearn.ensemble, import random, of course I spelled that wrong, and I need an N there, so random forest regressor. So a random forest is like a random tree regressor, but instead of just having one decision tree, you're going to have a lot of different decision trees. I don't know exactly how many the random forest regressor does, but it does a fairly significant amount to where it can heavily impact a model's accuracy in predicting your target. The next thing that we're going to import is from also the sklearn library in the metrics section, and we're going to import the mean absolute error, and this is a function to determine the average distance from the target that we're trying to focus on and what our model has predicted. Lastly, we're going to import something to break up the data, because when you are training your model and using predictions with that same data, you're going to get unreliable predictions when you compare it to similar data, because the data itself is trained on itself. So you want to be able to split it in a 70-30 split, where 70% of the data is used to train the model and 30% is used to validate the model. We first go in here and we store the file path into a variable. You don't have to. I just think it's a good practice. And I have it stored in the same folder as train.csv. Next, I have to store or at least create a data frame object. So we're going to go home data is equal to pandas dot read CSV, and then of course the parameter we're going to store as the Iowa file path. So now that we've got the data frame structure created, we can go and just do print home data.describe. So the .describe function pretty much gives you a table view of a lot of different statistics. So let me zoom out of the screen real quick and we can take a look at this data frame.describe. So as we can see in the output, we have 8 different characteristics for our data frame that help us understand our data. We have count, What count does is it creates a count of the total number of non-value areas. So for example, out of all of the pieces of data, there are 1,460 of them that are lacking an ID. The next one is the mean or average, and this is of course averaging the number that we are looking at. So for example, if we want to see the average year the home was built, we can see the average year is 1971 and some change. When it comes to things like ID, it's a little irrelevant, right? But when we look at like the lot area, we can see that the lot area on average is 10,516. So depending on what feature you're looking for, and I'll use that term in a little bit later, depending on what feature you're looking for, these different pieces of data will be important in comparison to these descriptors right here. We of course have the standard deviation next. We have the minimum, so the lowest value. So when we look at, let's see, for example, the year built, the lowest year built in this data set is 1872. We have this 25, 50%, and 75%. And these are unique statistics where essentially this is the number that is greater than 25% of the data. So, for example, when we have the year built, 1954 is or at least this specific house that's represented right here, is younger than 25% of the houses. Of course, when we look at the 50%, 1973 is younger than 50% of the houses. 75%. 2000, a house built in the year 2000, is younger than 75% of the houses. And of course, the newest house that we have is built in 2010. The next thing that we can do is we can look at the first 5 houses in the data. It's helpful, and we do, instead of .describe with our data frame object, we just do .head. And this is going to produce this output right here. So of course we've got these first 5 houses, and it'll give us all of the details about them. So for example, the lot area for the first house in the data set is 8,450 square feet. So this will help us get a pretty good idea of what we're looking at. So now the most important thing that we need to do is we need to determine what are we trying to predict. The purpose of this competition is to have the lowest mean absolute error, mean get as close as you can to predicting the sale price of a home. This is really important when you're looking for real estate market predictions, or you're at least trying just to get a good idea of how much a house will cost with a certain amount of features attached to it. A feature is a characteristic of your data object that contributes to what you're trying to predict. So for example, when we're trying to predict the price of a house, we want to look at how many bathrooms are in the house, how many bedrooms, how much square feet is in the house, how much is the lot area overall, is there a pool, is there an enclosed porch, how many of those are there. So there's a lot of different factors that go into influencing what the price will be. So the first thing we need to do is we need to store our prediction, or at least our target, what we're trying to predict, into a variable which is a lowercase I. So we're going to do home data, and we're going to do .price. And what this is going to do is it's going to look all the way to the right. So I'm going to scroll all the way over here. If you can see, the last item is the sale price. So we can reference that as price. And that's going to store into this Y variable. We then need to get a collection of what features are important to us. Now Kaggle, when you're walking through the tutorial on how to go about submitting your first competition, it gives you some pretty generic traits to consider. Those traits are as follows. We have the lot area, the year built, the first floor square footage, the second floor square footage, full baths, the number of bedrooms above ground, and then the total rooms above ground. And that was okay. If you ran through the walkthrough submission, you'd get a score around $22,000 of a mean absolute error. And that's okay, but when you're trying to predict a house price, $20,000 is a lot of money, and you want to make sure you're as close as possible. So for example, let's just say I was looking for a certain kind of house, and I wanted to know a good price I should make an offer on it. It'd be wise to use this model and get it as close as possible so I don't spend more money than I have to, and so I don't insult the seller by quoting a price that's significantly lower than what they might be expecting. So I improved upon the features that we have. So I added a couple, and we're going to store those into a list called features, which are as follows. We have the MS subclass, which honestly I have no idea what that means. We have the lot area, the overall quality of the house, the overall condition of the house, and these are rated on I believe, a 1 to 10 scale. The year built, the low quality finish square footage, enclosed porch, year remodel addition, first floor square feet, second floor square feet, and these ones below. I was able to deduce this by taking the original features that we had of lot area, year built, first floor square footage, second floor square footage, full bath, bedroom above ground, and total rooms above ground, and I started adding different features that were in the data set. Kaggle gave a long list of which ones won't produce an error because they're strings and not integer values, because they're strings and not numbers. And I started to deduce what would be my best mean absolute error. So I would test the data, I would train the data, I would test the data, I'd predict it, and the predictions would result in a lower and lower and lower mean absolute error until I came up with these features that I saw was generally ideal. So with that being said, we now need to store these features in a new variable, which is going to be similar to the y variable that we just created, but we're going to make it an uppercase X. And we're going to say X equals home data dot features. And this is going to store several series, it's essentially a subset of the data frame itself, which only contain the features that I've selected, which we're going to be able to use for our training the data. Now, like I had mentioned earlier, one issue that you run into with training your data is if you train your data, and then you try to predict the home price or whatever you're trying to predict off of that same training data, your mean absolute error is going to be really small. And that's because your computer is used to, and that's because the model is used to the training data. So it's really easy. Oh, I've seen this before. You know, a 3-bedroom, 2-bath with this and this and this is going to be this much. And it generally guesses pretty close. So what we want to do is we want to actually split the data up so we can have some data to work with. And the best rule of thumb when you're doing this is to split it 70-30. We can do that by using the train test split function from the sklearn library in the model selection part. We do this by writing train x val x train y val y equals train test split x, y, and then random state 1. There's a lot going on here, and I want to walk through that with you guys real quick. So essentially what we're doing is we're taking these 4 variables, train X, validation X, train Y, validation Y, and splitting the data up into a 70-30 split somewhere. I actually don't know if that's the exact amount, but that's what it was described to me as. So we have this random split in the data, and we of course have our X of features and Y right there for our target, and it's able to store the split of X and Y in these 4 variables. So we have our training data X, so we have our training data features, so we'll have a set of those, a training data Y, so we have a set of prices that work with these training X, and then we of course have the validation X and validation Y, which work with each other as well. This random state right here can guarantee us that we're using the same data. So when we're trying to improve our model, we want to keep using the same random state, because when we have that random split of how much data is going to be used for training data and how much data is going to be used for validation data, we want to make sure that same split is kept. Because if we just do a bunch of random splits, we're never going to be able to train our data effectively. So that's why you have that random state there. All you need to do is you just assign it to a number. So like for me, I just assigned it to 1. You can do it 0, 2, 3, 4. I guess you could do 100, but it's irrelevant. The point is you need to store a number in this random state parameter right there. Now that we have everything, or now that we have the data split, it's time to create our model. And we could do a random tree regressor, which would be fine. It's just a decision tree. But one decision tree isn't going to really help us too much. We want to do what's called a random forest, which is a lot of trees. So we're going to create our model, and so we're going to go RF model is equal to random forest regressor, and we're going to give it the random state 1. Remember, we want to keep using the same data split right here, and when we keep that random state 1, it just keeps everything consistent. Now we can go ahead and fit our data. So we're going to go RF model.fit, and we're going to put in train X and train Y. And what this is doing is it's fitting the model with that training data. So when we go to try to predict with it, we will be able to have the forest run and have a general idea of what our predictions can do. So now that it's fit, we can now take some predictions. So we're going to say random forest validation prediction, and it's going to be equal to random forest model.predict, and we're going to use our validation X to be that argument for the predictions. And now we're going to, so what this is doing is it's taking the validation X and trying to predict and it's trying to make predictions using the training data. And we're going to be able to see that in action in a little bit. So now we can do random forest validation mean absolute error equals, we're going to call the mean absolute error function and have the RF random forest val predictions as the first parameter argument and then validation Y. And what this is going to do is going to take our validation Y data and try to see, okay, how much off are we on average? So for example, like let's just say we have a prediction off by 2, a prediction off by 4, a prediction off by 6. Well, 2 plus 4 plus 6 is 12, and you divided that by 3, you're going to have a mean absolute error of 4. So of course, when we have that right here, we want to print out the validation mean absolute error for the random forest model. We can do this by having some fun string stuff. We go validation, mean absolute error for random forest model, and we can just do this. We go do some formatting. And just like that, when we go down here to print out what our mean absolute error is, okay, I see an issue. It's not y does not equal price, it equals sale price. That was my mistake. We can go down here and run it one more time. I'll clear the terminal. We can run it one more time, and we get 1,700, and we get 17,688, which is significantly better, in my opinion, than your 21,000 tutorial mean absolute error. This is not perfect. I'm still learning on more effective ways I could go about this, but with the tools that I've learned using the sklearn library, random forests, random trees, pandas in general, I was able to decrease my mean absolute error by a little under $4,000, which for me, I feel like that's a good improvement. I'm going to be keeping this GitHub repository open, so in the future, as I improve my submission scores, I can just update my GitHub repository, and we can all learn a little something together. I hope you enjoyed this video. If you did, leave a like, leave a comment. Suggestions for me how to improve are huge because this is something that I want to do with my career. So anyways, have a great day.